My name is Anshu Dubey. I work at Argonne National Lab. And so this talk, the next lecture, is going to answer a few of the questions that were raised by Catherine and a few of the issues that some of the students have also been raising through Jared's talk. And because it covers two sections that are important to software development. One is design and the other one is testing. And what I'm going to be telling you from the testing perspective is how to develop tests and how to design a test suite, rather than giving the definitions, etc. This is the obligatory license and acknowledgement, and so here we go. I'm sure, because I wasn't here, I'm not sure, but I'm sure that you guys saw this earlier in Catherine's talk. This is what the workflow for doing scientific computing, scientific discovery through software looks like. And this workflow it represents partial differential equations, but it applies across all kinds of science, because it is always true that you are starting out with somebody who's interested in some physical phenomena that is then turned into a mathematical model that is in some ways discretized, algorithms are developed for it, implementation happens, verification happens, validation happens. I don't know if the mapping of expertise was there in the earlier presentation of this, but this is the expertise one needs, is that there is a domain expert, science domain expert involved in transforming the physical world to the model. There is the mathematician and the domain experts that work together to do the discretization, applied mathematicians, and here it doesn't mean that it has to be a distinct person from the domain scientist. This is the expertise that is required. So it is very much possible that your domain scientist can also be an applied mathematician, but that expertise is needed to do to develop the numerical solvers and then do the implementation, verification, etc. takes applied mathematician, and then the validation requires again the domain expert to participate. But in high performance computing, the story doesn't end here. In high performance computing, it is also necessary to think about the optimization, the performance of the code on the target platform. And so we have this additional loop here which takes software engineering optimization experts to really get the software going on the target platforms. So the takeaway from this figure is that many different kinds of expertise are needed for majority of the scientific codes that are in play today, especially at extreme scale, right? And so this is what gives us the motivation for software design partly. One is that, of course, many of the scientific codes historically have developed by someone, a couple of people at best, doing something that they needed for their own purposes, and then someone else comes along and finds it to be useful. So they say, okay, this feature already exists. If I add this feature to it, then I can use it for my purposes, and before you know it, the software is accreting from all over the places in no systematic way, and so it gets to a point it becomes impossible to maintain, and then there is a hard reset and you start all over again, which means that all of the effort that had gone in developing the various pieces of software until now are completely useless. Not completely useless, you still learn so that the next time around your software development is somewhat more systematic, but still you still end up writing software again. Because it gets to a point where, at some point, your software gets to a point where the results that it is producing become questionable because it has accreted so much into it that you don't really know a way of properly testing it. And so what this does is it reduces software and science productivity due to technical debt. And I'm sure Catherine introduced the concept of technical debt. It is that it's a consequence of choices, in that when you do something quick and dirty, it collects interest, and the interest compounds, the technical debt collects interest in the sense that adding of next feature is much more difficult, and the debt compounds. As you add more and more features without paying off your technical debt, it just keeps on getting harder and harder to maintain the software and to use it for any useful purposes. Because it is, and I'm sure that this has been emphasized earlier on, is that it is, the science through computing is only as credible. It can be less credible than the software that's producing it, but it cannot be more credible than the software that's producing it, right? So that's why this is important. And this is a positive feedback loop that most of us in the business are facing these days in terms of scientific software development. It is that whenever you have more scientific understanding, see, you start out by taking a model, you simplify it as much as possible in order to get the first set of insights from it, which means that you use a whole bunch of approximations and you say, I'm not going to bother about this part of the code, I'm not going to bother about this part of the phenomena, and so on. As you get more understanding, the way you advance in your field is by removing those approximations one by one, which means that you get more terms in your equation, which means that you get more heterogeneous solvers, more diverse solvers as your model becomes higher fidelity. When you get more diverse solvers, you need more resources to run it on. When you need more resources to run it on, you go to larger and larger computers, which are getting more heterogeneous by the day. And so we have this perfect scientific feedback loop which just keeps on making our lives harder and harder. And then, in addition to that, the larger computers are rare resources, so it's our obligation to use them well, because you shouldn't be wasting no one really counts it in terms of money, but actually the money spent in doing your computation is extremely high, because the operational cost of these machines is huge, so wasting that computation time is really not a smart thing to do. And then the other part of it is that for most of whenever you're in this cycle, most of the components of the software, all the math solvers, the discretizations, etc., they're all subject of research. So they themselves can be undergoing change any time during the course. So what do you do? Where does that leave those of us who actually want to get science done on these large platforms with very complex codes? The first thing is that, so we have to think about software architecture in somewhat of the way that Catherine mentioned, that you have to think about some software architecture, but what kind of software architecture you build depends on the size and the ambition and the heterogeneity within your software. So the first thing you do is you take a stop, because anytime you do software process, testing, etc., right down to it, it is a tax on your software, because ideally if someone by magic could create your software which was working perfectly and so on, you didn't need to do any testing, you didn't need to do any architecture, you could just run the software and obtain your results. But that's clearly not the case, so you can view this process of designing software architecture and testing regime as an overhead, and its value really lies in avoiding technical debt. And so before you start to do this process, it is very useful to understand the trade-off that you're making. And so what you do is you need to be cognizant of your resource constraints, in the sense of how many people are there in your team and how much of their time is usefully deployed in making use of, in developing software, in developing architecture, design, and so on and so forth. So that ties into what is the target of the software, whether that is just you're doing something for the proof of concept, are you doing it for verifying some idea that you have, is it just exploring one single phenomena, and beyond that you're absolutely positive that you're not going to be using this software, whether you're doing it for experimental design, analysis, or else are you looking at something that is going to be living for a longer time and is going to be used by other people? What kind of user base are you looking at? All of that plays a role into what kind of architecting you do, and that should dictate the rigor and the rigor of the design and software process. Having said that, now I will focus on the most complex kind of software, which is the area in which all of us who are working on leadership class computing operate in, and that is multi-scale, multi-physics phenomena which take diverse solvers to arrive at the answer. So in architecting such codes, the desirable characteristics that we have are extensibility, because in 20 plus years of having been associated with scientific computing, I haven't known a single simulation where some customization of existing code was not needed. There always are customizations that are going on. So, and then portability, because even the same generation, it has always been case, but it's even more now true that even the same generation platforms are not identical. So if you want to be one of those opportunistic people who want to be able to use cycles wherever they're available, you need to have a portable code. Machines need to be used well, so you need performance. And of course, there is maintainability and verifiability for credible and reproducible results. And reproducibility is something that is really at the forefront of scientific discussion these days. More and more of the journals and conferences are asking for artifacts, are asking for some sort of a provenance, that the results that you produce with your software can be verified. There is something convincing the reviewers that sufficient care was taken in producing the results. But and what do these things mean? So extensibility means well-defined structure and modules and encapsulation of functionalities, because then it's possible to add another capability as an encapsulated capability, and you don't have to touch a whole bunch of rest of the code. Portability means general solutions that work without manual intervention. Performance is dependent upon being able to exploit spatial and temporal locality of data and minimizing the data movement. And maintainability requires clean code documentation and comprehensive testing. Ideally, we would like to have all of this done, but these are things that are non-trivial to achieve. In fact, some of these can be extremely hard to achieve. So extensibility, because when you have different class of solvers, the same data layout is not necessarily the best for all of the solvers. If you're doing hyperbolic solve along with a parabolic solve, then the hyperbolic solve is an explicit scheme. Parabolic solve is likely to be an implicit scheme, and if you're working with both kinds of solvers, what is good for one is definitely not good for the other in terms of how you're distributing the work. And also you have multiple operators, so different operators may have different load balancing requirements in terms of how you distribute work, etc., etc. In science, the complexity of a code, see, logically, whenever you're working with numerical methods, logically they tend not to be very difficult as long as you are in the main part of the domain, but all of them have corner cases that come out because physics is messy. Real world is messy, and so you have to deal with the corner cases, which add to the complexity, and they sometimes interfere with modularity, in the sense that if you're modeling these two phenomena using these two solvers, but they have lateral dependencies on one another, there is no getting around it. You have to deal with these lateral dependencies, and that's exactly what is difficult to modularize then. So these are the challenges to extensibility. Portability, there's tremendous platform heterogeneity, and because there is no convergence on programming model, and I think there isn't likely to be one anytime soon, at least until my retirement, one option to take is you do one implementation of your solver for each of the platforms that you might target, but that's a combinatorial explosion, because you have many different solvers and you have many different platforms, and you multiply them, and all of a sudden your code is looking like it can occupy the entire universe. Performance gets challenged because your solvers are what your solvers are. It's not, you can't say that because GPU is a cheaper resource that you should just offload everything to GPU. There are certain solvers, certain physics that just doesn't fit well on the accelerators. And so you may have a situation where you have small data sets on which operations need to happen, or you have low arithmetic intensity calculations, but that do have data movement dependencies, etc., and you can't always get around it. For maintainability, the real solution is, it is possible to do code maintenance, but its biggest challenge is the wrong set of incentives. The funding agencies will not make provision for somebody to do the maintenance of the code. The currency in scientific world is still publications and so on, which is at cross purposes with spending time in code and so on and so forth. So how do we tame all of this complexity? The biggest thing that comes to your rescue in all of this is separation of concerns. By separation of concerns mean think about designing your code in such a way that people with different expertise can sort of operate within their own area of expertise without having to know everything about the code. And codes get to a point where anyway no one can know everything about a code. So you have to be able to compartmentalize development in ways that people with different expertise can make meaningful contributions. And so this is the tack we take, is that we acknowledge that there are two different types of components in any code that we're working with. One set is subject of research, which is your model, your numerics, and so on. And this effectively should become the client code, as in mathematically complex client code. And then there are the more stable parts of the code, which is their discretization, I/O, parameter running, which is basically the backbone of the code and its infrastructure, and that controls data structure and movement, etc. So this doesn't change very often, and ideally your code should be designed in a way where that this part of your code design lasts longer than the platform life cycle. Whereas this, there's no way you can define in ways that it will span over life cycle, because the new discoveries come when they come. You can't plan for it, all right? So the thing to do is then to treat these classes of code components differently and hide one from the other, okay? But the things that remain common to both kinds of code development are that they should be encoded in logically separable functional units, which you can think of it as a code. And there are many examples that exist. For example, there is many of the frameworks that were developed during the 90s, for example, Samurai, I'm blanking, Cactus, etc., which they all operate on these principles that there is a whole bunch of components, and then you can, and these components encode a functionality, logical functionality, and are encapsulated in some way. These should be encoded into a framework, and within each of these entities, you should have a clear idea of what is different from public and private, and all of these units should be interacting with one another through interfaces of some kind. Even if there are lateral interface interactions amongst units, they should still be happening through well-defined interfaces, because that's the key to encapsulation. So a model that has been successful for us by and large, and I think it still continues to be successful, is this model where we look at infrastructure development separately from capabilities development. And so here more time is taken in upfront design. So this is the part for which, for instance, there is greater need to do things like requirements gathering, getting an idea of how do you want an upfront investment in long-term design. So this is where things like agile methodologies are not very suitable, but you may have to do much more of things like plan-based development, where you document it, you do testing, etc., of the infrastructure separately. And then there is the capability development, where typically your prototyping is this part, where you design, develop, validate, And then once you're confident that your capability is going to do what you want to do, and you can employ any kind of development process here, whether it is TDD or whichever favorite model of development you want to do, then you build the API on top of it, which then becomes known to the infrastructure, and then you do the integration where you augment the infrastructure so that this unit is recognized by the infrastructure. So this is the model that can let you do the kind of development that will retain some flexibility, modularity, etc., in your code. And this is the all of the currently successful multiphysics codes that are in existence. They have more or less, it may not be articulated in this way, but they have more or less followed this model of development. So the code that I work with the most, Jared and I work with the most, is called Flash. Flash has been in existence for 20 plus years, and it is used by some 6 or 7 communities that are as diverse as astrophysics to computational fluid dynamics and biomechanical modeling. What's common in them is that certain of the solvers that they use, the equations look similar to one another, so the solvers that they use can be composed in many different ways. And so this is an example of what a component of the infrastructure in Flash looks like. So grid is the unit that actually discretizes the domain, the entire domain. Flash is an adaptive mesh refinement code. I'm sure you've gone through, yesterday you would have heard about adaptive mesh refinement. So under the mesh in Flash is that, but also there is a uniform grid implementation. So this is in Flash parlance, this is the unit grid, which has all of the mesh functionality. Within grid, there are actually 4 different distinct functionalities that have their own subunits, and again they're well encapsulated. So this one deals with the Eulerian mesh, this one deals with Lagrangian data structures that exist that move on top of this Eulerian mesh. Under this sit solvers like the multigrid, the FFT, etc., that are used by many different functions, and then this is the boundary conditions. But under these, then there can be multiple alternative implementations for each of those functionalities. So there is well, these are subunits, and then these are the alternative implementations. And so when an application is getting put together, there is a configuration tool that can find out how to put these together, and so they are selectively picked, and an application is built. The other example that I want to show you is how to devise an API from a seemingly extremely complex functionality. So among the most challenging units that Flash has, not in terms of its mathematical complexity, not in terms of its logical complexity, but in terms of the services that are demanded from this unit by all of the other units, and that's the equation of state. Because units want to use it in a way where it's a standalone one single data point that you want to apply equation of state to, or because we are working with an AMR, you do a guard cell fill through interpolation, and then you need to make it thermodynamically consistent, so you need to apply equation of state only to the guard cells that have been filled at the fine coarse boundaries, or you just created a new block which got populated again through interpolation and you want to apply equation of state to that. So we need interfaces that provide all of that functionality. And also some of the physics just wants a single answer, some of the physics also wants the derivative quantities, and so on and so forth. So the way this was designed, this is the entire API of the equation of state unit. And some of these are, for example, let's see, this is the simplest one, which just does a single point conversion, single point calculation of equation of state. Many of these, like get data, get temporary data, put data, etc., they are just for manipulating data, for feeding it to this particular unit in a vectorized way. There is a whole system of masks, etc., etc. So, and then there are these helper functions, EOS wrapped, which are useful for non-sophisticated user, because what this does is based upon certain range of indices provided by the user, the vectors are automatically generated by to be fed to this particular unit. So all of this, what this has done is that equation of state is still invoked by other physics units as they need, but the data to be sent to them is configured using all of these helper functions, and there is an elaborate machinery of masks and defined constants that allows the information to be sent back to the physics unit that invoked this. So these are the kinds of considerations that go into designing the API for a model, right? Now, preparing for the future, what is happening is that the codes are getting larger and larger, and while it has always been true that the lifetime of a code is larger than that of a platform generation, now it is even more so. So it's much more important to do the design in a way that will last for a very long time, and the platform heterogeneity, because even the next generation platforms that we are planning in 3 different DOE labs, the Berkeley, Oak Ridge, and Argonne, there is very little in common in terms of their architecture, except for the fact that there are CPUs and there are accelerators, but the CPUs as well as accelerators are completely different in flavor from one another. And so what's a code to do, right? The only code that can be done is to deepen is to lift abstractions and deepen the hierarchy so that there is much more composability left within the code for being able to tackle the situation. So the way and I'm specifically going to talk about how we are approaching this for Flash, but that doesn't mean that is the only design that exists. What you should take away from this is much more the methodology rather than a specific design of how we go about doing this. So in Flash, what we say is we differentiate between the physical, the real and the virtual view, which makes the simpler world view at both ends, and it's much easier to design for it that way. And then we make hard-nosed trade-offs. So, and then what we need to think about is at what granularity do we want the components to exist. So in Flash, up until now, components have been at the granularity of a unit, a functional unit, or its subunits. At best, there have been 3 degrees, 3 levels of hierarchy, subunits. But within that, there are kernels that are relatively big and complex kernels. For the forthcoming platforms, that is no longer enough, which means that now we take the granularity of composition much lower, and now it needs to come in form of, for example, a kernel can be a very overloaded work here. A kernel can be, in accelerator terminology, it is the function that you're launching onto the accelerator, but in Flash terminology, it is the part that actually does the arithmetic calculations. So now, what is a Flash kernel needs to be broken up into what are accelerator kernels, because you want to be able to compose those as well. And so now we can view them as tasks. And then there is this idea of what tasks should be going to what device, whether it goes to CPU, accelerators, and because we don't want to design ourselves into a corner, if other kinds of devices come into play, we should still be able to exploit them. And so we have to think of a design in terms of mapping tasks to various devices, and how do we manage the data movement between devices. So the past design has been that the real view is a whole domain with many, many operators, and here by operator I mean a physics capability. There is the functional decomposition and there is the spatial decomposition. Functional decomposition is in terms of different operators, and the spatial decomposition is in terms of blocks in an AMR. This is a structured mesh block, so these are blocks in the AMR. So in a virtual view then, it is a domain section as a standalone compute unit. A block surrounded by its ghost cells is a standalone computation unit, where an operator that's operating on it cannot differentiate between just that block and the entire domain. As far as it knows, it is operating on the entire domain. the functional decomposition, the virtual view is as a collection of components. And so the memory access and compute optimization happens at the level of the component, whereas the scaling and parallelization optimization in distributed memory model I'm talking about here, in the previous versions of the code before the accelerators came into being, was at the level of spatial decomposition. Now the picture changes, and so now what we have is abstraction at solver level, and abstraction at solver level means that we have further decomposed the flash kernel into these tasks that are within, that exist within that kernel, but these are the tasks that are sort of bookended by any data movement that needs to happen. And therefore, these tasks now can be offloaded to another device, be it accelerator or some other device, or it can be decided that this task operates on the CPU itself. And then we can make use of code transformation technologies, and this is the key part, is that because we don't have a converged methodology for doing code transformation right now, as the software designer, what's more important is that we write our code in a way where whatever kind of code transformation comes along, that we should be able to plug it in rather easily without having to rewrite the code in a big way, which means that this abstraction has to be done right. And that happens, and then that can do the optimization for memory access and computation. Many such things exist. For example, Cocos, Raja, and then there are auto-tuning tools that are coming along. But unless one designs software to be able to do it in such a way, any use of these codes can become extremely intrusive to your software and therefore not very useful. Like many people who are adopting Cocos and Raja now have to rewrite chunks of their code from scratch because it will only work in a C++ mode and so on. And then within the collection of components is now broken up into much smaller components, again, so that there is greater flexibility in scheduling it, so that there are tools that can either do fusing of functions, that can determine whether fusing of a function is a useful optimization or not, and then can do the dynamic scheduling, and that is partially doing the parallelization and scaling optimization, and partially doing the memory access and compute optimization. So this is the methodology that I'm saying is what I want you to take away from this particular lecture, is that this is how you go about doing it. So the flash approach is that the discretized whole domain and multiple operators is the whole code. And then what we are doing now is we are applying constrained semantics in the sense of dividing, instead of having loop nests, for example, they are getting turned into functions, so that each of those loop nests can then be handled by a code transformation. So when the main code is written, it is just written in the form of invocation of these various functions. If you want to call it our own domain-specific language, you can call it that. But the point is that because we are defining our tasks in terms of these much more coarser grain operations, where the details of how you access data are not left to the programmer who's writing that code, what can happen is, one is that many a time compilers are not able to do a good optimization on the code, because people, when they're writing the code and they're not aware of how the compilers do their optimization, they can write code in ways that blocks optimizations. So writing code in this coarser granularity with constrained semantics prevents that from happening, for one, and second is that you can incrementally apply code transformation function by function as needed, because these things are now sitting in as their own entities. And so with this constrained semantics, then we can do the memory access and compute optimization, as well as parallelization and scaling optimization as needed. And so here is where we are seeing that the AMR infrastructure, for example, is taking care of, because it takes care of refinement, load balancing, and work redistribution, it will take care of scheduling, dynamic scheduling, load distribution, and parallelization and scheduling. And the virtualization of components because of the code transformation, fusing and inlining of function, etc. These are the abstractions for performance portability, and these are the ones that are going to be doing the data orchestration and memory hierarchy management through a tool that will be able to take that way. So the way we are planning to do it is we construct the operators in form of appropriate abstraction. We specify part of the domain and condition under which these operators apply. We have mixed mode parallelism, but the important thing is that there are smart iterators that are aware of mixed mode parallelism and dependencies, and these dependencies we can encode in any form of meta information that can be read by the scheduler, and then basically this happens by that the iterating loops give up control, and instead of doing explicitly saying go one block after another, they just say give me a block and I'll do it. So it's a very small difference, but it enables the schedulers to be able to work with the existing framework instead of having to transform large chunks of code completely. So these are all this is the list of efforts. I'm not going to go over them. You will have them in the slides. But the other things to consider are leveraging existing software, for example, libraries, because sometimes they may have better solvers. There are many packages that are attempting to achieve interoperability, so it may be worthwhile to let the library dictate data layout if the corresponding abstractions dominate in your code. But whatever you do, it's extremely important to institute a vigorous verification regime at the outset of whatever you're doing with your code, whether you do it in form of TDD or test supported development or whatever you want to call it. And with that, I switch over to testing and verification. Any questions on the design part? Yes?
Well, this might be a little bit too specific, but in terms of libraries, like let's say, just taking Flash as an example, that you were trying to develop a new module in Flash or like a new solver. Is it like, if you want to use a certain library just like in your one solver, is that like okay to do, or is this like something where it's like the library should be something that is used by the whole framework? That's kind of my question.
So, a better answer always is that if you can figure out a way in which the library interoperates with the data structures owned by the whole framework, that's better. That's always better, because this has been our experience in the past, that we stick in one solver for one specific problem. Somebody, other domain says, oh, great, we can use it for this purpose. And so then they go ahead and use it. And if you've embedded a library access within a unit, then it's not accessible to the rest of the code. So yes, so ideally you should think of design, invest some in design, do it in a way where it's generally accessible everywhere in the code. If you can't get away with it, and if you don't care about making it available to the rest of the code, you can always do it within the unit. It's your choice again as to what you want to do with it. Any other questions? Okay, we move on to testing and verification. So verification is something that uses tests, though it is more than the sum of all the tests. It is the method by which you convince yourself that your code is actually doing what you want it to do, and that you are going to produce the science with it that you want it to do. So verification can come in many flavors. Of course, you have to do verification during initial code development, because otherwise how do you even know that you have produced a code that is going to do some useful work for you? So you need to verify when you're working with numerics, you know that you always need to verify it for accuracy and stability, and you need to check out the regime of operation in which that thing is valid. You absolutely should be documenting that also. You should be matching the algorithm to the model, and then if you have model that needs many different, that has many different terms, say in a partial differential equations, you need to make sure that all the solvers for these various terms can interoperate with one another. When you're in the later stages, when you have a stable code, then you need to do verification for maintenance, making sure that whatever additions you're making to it are not breaking the code in some sense. And of course, you will always be adding new major capabilities, which means that when you're adding it and you're integrating it into the code, again, you have to make sure that this major new capability interoperates with things that it needs to interoperate with, and that it doesn't preclude some other prior parts of the code from being usable. And then there is the verification in preparing for production, because that is a complete different beast, and because I'm slightly short of time, I'm not going to go into detail of that here, but if any of you are interested in talking about that specifically, I'm around today, and during lunch or during any break, I'll be happy to talk, because preparing for production verification is a very specialized kind of verification. Not all projects do it, but it's critical for good science to do it. Anyway, there are and when you're trying to do it with exploratory software, so you know that there are reams and reams of papers written on paper on testing and verification in enterprise software. Now, the little known fact is that all of this process works on an enterprise software because there are whole teams available to do this. If you ask the question of even big companies like Google, what happens in their research departments, and they don't have a good answer. Because in their research departments, the software that is getting written for exploratory purposes. And so, but the real filter that they have in existence, because of which that software doesn't ever end up getting a bad name, is because nothing coming out of the research department becomes a product before it is filtered through this process of software verification that is instituted for any product that goes through, right? So these challenges exist with exploratory software everywhere, where you don't know what the outcome is going to be, and you have to somehow verify for correctness without completely knowing what the outcome ought to be. In our case, in scientific world, the research department is where the production software is coming out of. There is no filter in between to do the quality verification, which means that we need to be our own gatekeepers in some sense. And we need to therefore figure out how to do the verification in a way that convinces ourselves and the people who are doing reviews of our work that this verification is adequate and that the results can be believed in some ways. There are all of these other challenges that exist, and I'm not going to read through them because, again, you have the slides and you can read about them. But specifically, there are challenges with legacy codes, and this is one of the questions during Jared's talk had addressed this one as to what do you do when you have code which may have been tested when it was originally developed, but the tests that were developed with it have been lost in the midst of time, and then there is no documentation. You don't know how to go about testing it because the expertise also doesn't live with you. And so one of the big challenges that we have found over and over again is that not only is it that you don't know how it's interacting with various sections of the code, but then there are times when it seems like really bad code that you're really tempted to just yank out and get rid of, except that when you yank it out and get rid of it, it stops functioning appropriately. So it was there for a good reason. And so it's really difficult to differentiate between a valid bad code and a bad code. And in this situation, and code coverage tools are of very, very limited help because they don't tell you anything about these interoperability, et cetera, et cetera. So to step back a little bit, components of verification are testing at various granularities, which means that you want to test for individual components, interoperability between components, convergence, stability, accuracy, and then things that one should know are things like error bars, because if you are doing anything in parallel, the bitwise reproducibility of any answers is not guaranteed, because there is always I mean, as soon as you have a parallel reduction in your code, you cannot do a bitwise reproduction, bitwise matching of your results against any benchmark. And an important component of it is selection of tests for coverage, and I will talk to that a little bit later. I'm going to skip over this slide because I'm running out of time, and you can read this stuff also. Right. So this is the part which I want to spend some time doing. Development of tests and diagnostics usually goes hand in hand with code development. And Jared said that, because he does test-driven development, that he lost his chops in debugging. Let me tell you something. Even though I haven't done explicitly test-driven development in my 20 plus years of developing Flash code, and there was a time when there wasn't any part of Flash code that I hadn't touched in some way or another, I've used debugger on Flash precisely twice. And that's because anytime I need to find I need to debug a code, I actually sit down and think about what kind of a test can I build that is going to be able to pinpoint that bug for me. And that takes more time up front, but then the process of narrowing it down becomes very, very simple. So in that sense, and I assert this to be true, is that I've always taken, in general, the quality of the software is driven by the quality of the tests you can devise for it. Because it forces you to think about what are the functionalities you're putting into your software. Okay. So now, when you're faced with a legacy code for which there are no existing tests, these are the steps you go through, and I will demonstrate it with an example from the climate model community that I worked with a scientist on to devise a legacy test for one particular model. So the climate community is the E3SM. It is DOE's attempt to put together all of the people working in the climate modeling community into one large code base. And they spent a lot of time building software engineering practices for it, tests, etc., for it. In the process, what ended up happening was that a whole bunch of code modules, so this is all written in Fortran, and there's a whole bunch of code modules that have the state variables and other parameters that the codes are dependent on. And the idea is that whichever part of the code wants to get whatever of this state as well as other parameters should just say include this module and run with it. What that ends up doing is it creates a serpentine dependency. Because you are in this part of the code, you are dependent on something, that something is dependent on something else, and then another something is dependent on another something else, and all the way the dependencies go all over the place. So even for simple debugging, what people end up doing is they run the whole model, the entire big large model, and to run that, then they need to submit it to some cluster or some such thing, because it won't run in a small area. And so the turnaround time was in terms of number of hours. So this is what the code looked like a little bit. So what we did was we said, and this particular model that we wanted to test was just a column resolution for the atmosphere. So there was no reason why it should have had to run in the middle of a whole big chunk of code. So what we did was we separated the section of the code that we wanted to test, just isolated it, created a subdirectory where everything at that level and below was copied over, took a state snapshot of a whole model run just before it feeds into that section, wrote a driver that would just drive this part of the code, and looked for dependencies. So if there were dependencies that were hard dependencies, we copied over those files. If the file did not need any modification, we just created links to those files. but we wanted to also prune the dependency. So some of those module files we modified by eliminating dependencies from them and copied them into the driver. Wrote a reader for the state, and then was able to run this in a small test. So the steps were: isolate the part of the code that we wanted to test, right? Take a state snapshot, copy the, link in the files that do not need modification from the rest of the code. Where you want to prune the dependency, copy the file and eliminate the file lines that were causing that dependency, and then write a driver. This test now runs in a matter of 20 seconds on the laptop of the developer. So this is what a technology using which you can develop, methodology using which you can develop code. And so now you can just restart from the save state and you can run this test. Then there are the questions of granularity, because in scientific code it doesn't always help to have unit tests. You can't always have meaningful unit tests for everything. So what you do is you build granular tests. So you approach this problem sideways. There are components that can be exercised against known simple application, test them that way. Build a scaffolding of verification tests to gain confidence. So what we have is, we have a unit test that can be a standalone unit test. If you know that this unit test is working, then this part of the unit test for another unit is dependent on this unit test, but some part of it is not dependent on any other part. So this is a mocked up dependency, and then this particular unit test is dependent on the outcome of this unit test. Example again, because this can be confusing. Example from Flash again. So there is a unit test to verify the guard cell fill. You fill the interior, so this is the interior, this is the exterior, right? Take an analytical function, have two variables. One variable just gets the interior filled, the other variable from the analytical function, the other one gets the guard cells also filled. On the variable where only the interiors are filled, you apply a guard cell fill process, answers should match. This is a standalone unit test. So it's this variety of unit test. There is similarly an equation of state unit test, which is this variety of unit test, where you just run it in different modes, where output from one mode becomes the input to the other mode, and so on. And at the end of it, all of the variables should be self-consistent, and you have a unit test that is a standalone test. Now, using those, we can create a unit test for hydrodynamics, because in hydrodynamics there is an analytical solution for a blast wave in terms of how far it goes out. But it isn't a standalone unit test, because it depends upon grid as well as equation of state. So if grid and equation of state unit tests have passed, and then this test also passes, then this becomes a unit test for hydro. So in that sense, it is this kind of a unit test where it has built upon, it has built upon the grid passing the test and the equation of state passing the test, and now it has become a unit test for hydro. But then there are other aspects of it. In that, with AMR, there are other functions that haven't been verified yet. So those functions are, for example, for flux correction and regridding that haven't been exercised. So now you start to reason about it. You run the code with the uniform grid, you run the code with AMR, you run the code with regridding turned off, and you run the code with regridding turned on. In all of these situations, now we have isolated one particular possibility of a bug, in that if you run hydro without AMR and if it failed, then the test is in hydro. If it ran with hydro but failed with AMR, then and no dynamic refinement, then the fail is in flux correction. And if all of those pass and it fails only when we do regridding, then the fault is in regridding. So this is how you build a scaffolding which tells you how to build the, how to gain confidence in your test problem. And then there are, for selection of tests, there are tests that you need for regression testing as well as continuous integration. One of them, the regression testing, can be much more comprehensive. Continuous integration need to be small by definition, because if it's taking too long to run, it's not going to be particularly useful. And this, I think, is going to be covered much more in detail later in the afternoon, so I will skip over that. The rules of thumb are that the test should be as simple as possible, should be taking as little time to run as possible, and they should enable quick pinpointing. So again, and why should you not use the most stringent testing? Because again, it is a tax on the team resources. So if you're applying too much tax, then you can't do any productive work. If you're applying too little test, then the defects will go through that should not have gone through with due diligence. So a few points: unit testing is always good, but it's never sufficient. Understanding the range of validity and applicability is also important. Well, I want to move over to how to build a selection of tests. The way we do it in Flash is build a matrix where we say that we have all physics along rows, all infrastructure along columns, or vice versa, whatever the case may be. We pick tests, the setups. So Flash comes with setups, which are predetermined applications, and you can run them in smaller set with parameters controlled. And so what we do is we pick tests, all the unit tests, and then we pick tests that represent ongoing production, sensitive to perturbations, etc., and we fill the matrix in this way. So here is an example where the SADA of test exercises uniform grid hydro equation of state, and so it marks off these things. The cellular test exercises hydro equation of state, burn and particles, and so on. So for each test, we mark off in the matrix the capabilities that are exercised and keep doing it until this matrix is filled, and that gives us a set of tests that will more or less exercise the whole code. So with that, I come to the end. The takeaways is that whether you're doing design or you're doing tests, it is important to understand your need. It is important to do cost-benefit analysis, adopt whatever works for you, don't design yourself into the corner, and verify, verify, and verify. Questions? Did I do too good a job or too bad a job?
I have a question.
Yes?
It's quite generic, and I don't know if it's a little beyond the scope of today's talk, but I was wondering about this testing and development section.
Yeah?
Do you see that this kind of modular approach, or rather I should say kind of modular thinking, only dealing with research-based codes that are being handled at universities or research labs, national labs, or I mean, how do you see? Do you see that there should also be a reason that this should be incorporated in more in academia, or more in low-level frameworks? For example, in graduate courses, where I think development of codes and this testing and verification idea doesn't really go hand in hand.
So if it were up to me, I would do this everywhere, right? Because people adopt in their professional life what they did as students, and I have seen that wherever the curriculum or a class takes into account these kinds of practices, that the students end up using them forever, or for that matter, all of Flash's alumni use the coding practices we have had in Flash, even when they went on to become professors elsewhere and had students of their own. They have asked their students to follow these practices because they saw the value of it. Our biggest challenge has been that the people that we can sort of indoctrinate, like people like you who are coming to these classes, are not the people in position of deciding the policies for the departments, right? So that's why it's been harder to get hold in academia, because it's the professor who has been doing this thing without all of this software process for 30 years who doesn't want to listen and doesn't want to change in any way. But really, so you guys are the future professors. Take it away with you and make sure that you incorporate good practices in your own professions. Any other question? All right. So